Hello everyone, welcome to my AMC 1012 Common Must-Know Impact Concept Recap class. Right, so there must be some people who already know me or some other people may not know me. So I'm going to tell you what this class is all about and who got to take it and what I'm teaching in this class and why you guys have to take it and what we can expect from this particular class. Right, so here we go. For those people who are about to take this lecture, well, they got some common symptoms, right? So those common symptoms are going to be something like this. I labeled it as like 1, 2, 3, but the first set of people that I found out was having this type of problem. They have solved past problems already, yet they get some questions about like 10 to 15 correct, but not really getting above like 18 to 25. But of course, I'm not saying that we should always get the last 5s or even the last 8 questions. But what we're saying is that you should actually have solved those practice problems and always maintain consistent level of, the correct questions. However, if you have to have some kind of huge gaps between those, like the AMC 10 2012 and AMC 10 2017 and whatnot, you might have had this type of symptoms. Well, this class is perfect fit for you. And the second type of people that I've noticed is that they are able to solve some given problems. But sometimes, they are not so sure whether they were using the right strategy and whatnot. They're not so sure when to multiply. They're not so sure when to add. And they use some different strategies and they looked at the AOPS solutions, but they're not really getting some, the insights in those ideas. And they're not being able to figure out whether those solutions can be used to be, they can be applied or applicable to the other set of questions. Well, those are the second type of people that I've noticed. And the third type of people are something like this. They're already familiar with most of the concepts that are laid out. They know. They have learned counting. They have learned probability. They've heard about circles and bars. They've heard about some, permutation allowing repetitions. They heard about Bezout's identity. They heard about Brahmagupta's formula. They heard about some cyclic quadrilaterals. They know some of those concepts already in terms of just concepts, but they're not really being able to apply those, the problem-solving mechanisms onto the set of problems. Or even, not limited to just basic problems, but also, containing all those problems in the last 5s. Well, there must be some questions that we can tackle in the last 5s. And there must be some questions that we can get those questions correct. So over that, for that particular reasons, I set up 3 possible scenarios. And if you have these symptoms, this lecture series is going to be a perfect fit for you. Right. So why am I lecturing this? And, the purpose. Of course, I want you to get really, really good grades, solid, qualification scores. But at the same time, having taught so many kids out there in AMC 10 and 12 in this, and Amy in Apgujeong in the past N years. Well, when I said N years, it's about 10 years and whatnot. Well, having taught so many kids, I've seen some people who already are perfect, who are already fit for getting qualified. And I've seen some people who are not ready to get qualified, but I've, helped them getting, their all those knowledge, completely filled in. And they can finally get qualified into those, the Amy qualifications. And they went to solid, nice niche colleges. Now, having said this, I've gained some valuable insights of problem solvings. Well, I wouldn't say that I was a perfect problem solver, and I wouldn't really say that I'm still a perfect problem solver, but at least I can teach you about those insights of how to get some, some questions that you always need to get correct in order to get qualified. So I want to actually hand you over those missing puzzles. So when I say missing puzzles, I'm not here to give you the dilemma. I'm here to give you that missing part that you've been searching for. Well, you try to listen to a lot of the lectures online or offline, but if you haven't found any, some good parts that's filling you in terms of the knowledge-wise, this is going to be perfect fit. And in fact, I'm actually here to guide you out from the dark tunnel that you have, you've been passing through so far. Well, the dark tunnel makes you actually feel that the concepts, well, not in, the concepts in general, but not really. Not sure when to use and when to use whatnot, or those, like those specific knowledges into details. Am I going to use circles and bars? Am I going to use partition of natural numbers? And am I going to, use like Pythagoras? Am I going to use law of cosines? Well, what are we looking for? Are we looking for lengths? Are we looking for, those angles? And man, what am I going to use? Well, in that situations, well, I'll help you figure out what to use, and I'll guide you perfectly well to get you through those tunnel. Okay? So here we go. What are we, what do I have in terms of like materials wise? Well, am I using the past materials? No, I'm not using any past materials. I actually had hand-tailored 100 problems. So I made all those 100 problems penetrating the deepest core of AMC 1012 past problems. So what I'm saying is that if you solve these 100 problems, you will be able to solve most of the, most of the problems that you see or have seen in the past AMC 1012 problems, around about up to at least up to 19. Well, there are some questions still. There are some questions in the last fives in AMC 10 and 12 that are pretty tricky, and they're really hard. And normally when you are in the actual real testing setups, you guys won't be able to, you guys will not even bother solving it. You guys will leave them blank. However, other than those problems, most of the common types of problems that you got to face or you will experience during those test preparations, you guys will be able to solve most of the problems by going over these 100 tailored problems. But at the same time, well, here's what's up. For those people who were taking my offline lectures, this is going to be a good, concept recap. This is going to be a good revision materials for most of the stuff that we've been going over for those weekend classes and for those summer classes and whatnot. When we have those, when we have taken those classes out there around about 6 weeks or 8 weeks in, with time intervals, well, this is going to be a good material for you to practice and revision all those materials that we've covered so far. Okay, so what am I covering? I have 4 major topics right now. I got combinatorics, aka counting and probability. I have basics to intermediate, but not limited to, including but not limited to Burn's-side lemma. That's right, I got Burn's-side lemma right here. In geometric probability, well, I try to set up the geometric probability only up to the two variable situations. If you can extend up to the 3-dimensional, the 3 variable situations, you can expect volume questions, and current up-to-date problems were actually involving some, volume ratios. But right now, so far, up to 2018 and 19-ish problems, but still we have those geometric probability up to, 2-dimensional applications. But at the same time, I do have linearity of expected value. That's right. I have state, and also I got some recursions, so you can actually learn most of the materials that you've seen in AMC 10 and 12, but not being able to see it in the conventional type of problem-solving, prep books that are currently sold in South Korea. Now, the second one is number theory. The number theory, I also have lots of basic materials up to intermediate levels. Of course, Fermat's theorem, Wilson's theorem, Euler's theorem, Bezout's identity, Chicken McNugget theorem, all those main identities, and GCD and LCM application only targeted specifically to solve the up-to-date problems. So if you are looking at some past problems, you wouldn't have been able to see some GCD and LCM applications, but the current problem writers actually like making some GCD and LCM problems. Well, I have all the techniques laid out in this number theory part, and you can also see those things in plane geometry as well. Plane geometry, I try to make this as simple as possible, but also I try to become the current problem writers, and making all those problems according to his style, so you guys will actually see very, the questions that are very similar to the current level, the current year up-to-date problems. Not just limited to just AMCs, these questions are very similar to ARML and CMIMC and all those the HMMT and SMT and PUMAC, all those major competitions do have certain set of rules that they are, I don't think that they have the common agreed, the backgrounds or so-called the bottom line in order to make some problems. But I think that they want to, when they ask about lengths, you got to know about some specific details. When you're asked about to get something about lengths, the angles or areas, you got to know about some other details of trigonometry. But in this class, I'm just only focusing on AMC 10 and 12 common parts. So I'm not having anything about main trigonometric bashing. But again, we do have some setups that can be used instead of using trigonometry, but being able to solve those problems using just Pythagoras and probably just basic law of cosines. Anyway, that's plain geometry. And what about algebra? Algebra. Well, people who are taking algebra, well, you might belittle the importance of algebra. I do have some AMGM inequality and power mean inequality. If you have no idea what power mean inequality, you got to take this lecture, man. And if you have no idea what Cauchy-Schwarz inequality, you got to be able to use Cauchy-Schwarz inequality. And these are the set of inequalities that we're using instead of calculus to get the minimum and maximum the maximum value, especially when things are given in the real number system. So algebra is also a little bit different from algebra 2. And even different from pre-calculus. However, this is specifically targeted to AMC 10 and 12 / AME. Okay, early AME. Not the hard AMEs, but early AMEs. Right, so results. What are we really expecting here? Well, we're expecting something. Like your future self, strong and confident in the real testing setups. So in your actual real testing setups, when you're taking the real exam, I want you to be strong and confident. I gotta be self-resilient. I gotta be really resilient though. I don't want you to panic in the exam not knowing what to use and whatnot. I want you to stay calm and be able to solve it. In order to do that, well, we're gonna bring self-confidence to another level, okay? And here's the last thing that I want you to try. We're not gonna solve all 5 problems. It's impossible. It's impossible to solve all 5 problems, last 5 problems on time. I don't think that's possible, realistically. If you guess and get them correct, probably, but I don't think that's possible. In order for you to do really well on those last problems, I want you to just do that or show your, full potentials in AME. Why not? You got more than 3 hours to do so. But we only got 75 minutes to solve those 25 problems. It wouldn't be enough time for you to do it. So we're going to solve some of those. I'll make sure. Well, that was my goal so far in my offline classes that I've been teaching. Well, I want you to solve some of the questions, not all questions, but some of the questions. It can be 1, it can be 2. Some of the questions in the last 5s with certainty. Some of the questions, of course, at least 1 question in the last 8 questions. So that if you try to solve those questions from 1 to 15, and you stop and you move on to the last 8 questions, you try to see what type of questions that you can solve, and you try to gauge what level of questions that you can try out and try it out. And if you get those 2 or 3 questions correct in the last 8, well, pretty much you will get qualified, right? So that's my goal. In fact, I want you to stay resilient, strong, and confident in the real testing setup. Okay? So that being said, this was my introduction to AMC 1012 Common Must-Know Impact Concept Recap. I'll see you in the lecture. Hi everyone, this is the first lecture of Must Know series. We go with question number 1. Right, so here we go. Question number 1, this is the first question of the whole series, I guess, and I would like to talk about just the basics of countings first, which is multiplication principle. Right, so when you go over the principles of multiplications or principles of addition, the first thing that we have to learn is the sensation when to multiply or when to add. Well, multiplication versus, I guess, addition. And of course, as of a title of this question, I just called it as multiplication principle of counting, and / I wrote it down as ongoing action. So I want you to write down notes, and I'm going to give you 2 particular solutions for this question that you can use and you can learn for these types of questions. And of course, like this question itself is not that crazy hard, but you just got to understand when to add and when to multiply. Right, so here we go. So this is going to be the notes. When do we multiply and when do we add? I think we gotta learn, we gotta distinguish between those 2 principles. First, we multiply when things are having under successive events. So in other words, events are successive. So when events are entailing another events and so on, then we keep multiplying. Well, I usually say these are ongoing action. This is my phrases, ongoing action. So whenever you start counting, you got to ask yourself whether my counts are finished. If your counts are not finished, then you got to keep multiplying, okay? But however, the addition is going to be a little bit different. It's going to be something called casework. And I normally call this as a casework, but at the same time, we perform the addition principle when futures changes, when the structures are getting changed. So you got to think about the Doctor Strange in, like the Avengers series, the last Avengers series. If you think about Doctor Strange, he sees all the futures of winning against Thanos. And when you see, when he sees all the futures, there must be some future when, like the Iron Man doesn't die. And there's going to be a future when Tony Stark actually dies. And he found that Tony Stark has to die in order for the world or whatever to be, salvaged, right? So, in other words, when we perform casework, these are thinking about some kind of multiverses situation in a Marvel series, so to speak. It cannot happen at the same time. It'll be, it may appear in some other possibilities, but it's just not going to be happening at the same time. So physically, it may not happen at the same time, or you got to think about either A or B. So it's going to be something like either or at this, in other words, those structures are actually getting changed. Futures get changed. When you keep, using some kind of making certain choices, then future changes and you got to keep adding, okay? So here's what's up. Like future changes. It's so just too much of a literary census, but I'll give you the explanation of this question by going over two solutions. So solution number one. I want you to start writing it down. Of course, you got to write down the notes. These these lectures are actually the last revision before the AMC 10 and AMC 10/12. So solution number one goes out like this. We got, there are two types of pants and two types of shirts, and one can buy all or not. In how many ways can one buy the clothing, if any? So here we go. Pants one and pants two. Right. So first of all, I want you to think about how many, choices that you got. Well, first off, you can think about choosing nothing, or just choosing one pant and choosing two pants, the second one, and choosing all. Does that make sense? Are we multiplying this? You can think about it. We got one choice of choosing nothing. I got one choice of choosing the first pant. I got another one choosing the second pant. I got one choice of choosing all. And if you think about it, of course, you are normally saying that, hey, we got four possible cases. I understand that we got four possible cases, but why four cases, though? Because if you think about it, choosing nothing happens in multiverse 1. Choosing the another one happens in multiverse 2. Choosing the third possibility will happen in multiverse 3. It's impossible for you to choose pant 1 and pant 2. It's going to be something like, think about Spider-Man 1 existed in one world and Spider-Man 2 existed in another world. So these possibilities are all happening in different possible universes, so to speak, in Marvel series. And it's going to be four cases, I guess. Right, so now we got to ask about the questions. All right, so I got four cases. I got four possibilities of choosing, some pants. Now, am I done with the counts? Well, if you think about it, I'm still having shirts left. I need to think about something that happens under the shirts. The same type of possibilities will occur. We're not done with the counts, so we got to keep multiplying, but forget about those multiplications. We just think about those separate things, one at a time. One at a time. So shirt 1 and shirts 2. So we got empty set, choosing nothing. And by the way, these are the empty set. These are, this indicates that we're choosing nothing. Or maybe we can choose one thing. Maybe we can choose the other. And S1 and S2. We got four cases as well. Now, guess what? What do? Are we adding or multiplying? Got to think about it. You chose something for pants. And you're asking yourself, am I really done with the counts? Oh, what about the shirts? Oh, I didn't choose any shirts. So you got to keep multiplying. So that's what's up. This is 4 times 4. So this is going to be resulting in 16 possible cases. So the answer are going to be 16 cases. But what about solution 2? If you think about solution 2, well, you can think of, you can think of all of these scenarios and just, in the whole, as a whole, as a big chunk. So I'll give you the explanations right here. So P1 and P2 and S1 and S2. If you read the question carefully, this person can buy everything or nothing, right? So we keep asking ourselves this question. Hey, P1, am I willing to buy P1 or not? How many choices do I have for P1? I got two cases. I got two options, buy or not. Buy or not. So I got two options, right? I got two options for P1, and you got to keep asking yourself this question during the actual exams too. Hey, am I done with the counts? What about the choices for P2, S1, and S2? I still haven't made any decisions about P1, like P2, S1, and S2. Well, you got to keep asking the same questions. We got two choices as well. And you got two choices, and you got two choices as well. Two choices and two choices. And this is the sensation of ongoing action. You made a decision for P1, and you're thinking, am I done with the counts? No, I'm not still finished with the counts. I got to keep multiplying something. I got to keep thinking about some choices for P2. Well, there are two. So you keep multiplying. 2 times 2 times 2 times 2. Oh, so that's why we get 2 to the power of 4 and 16 cases. Okay, so that's the first question that I wanted to cover. I already spent some time on here, but I think this is quite important. Right, so that being said, let's move on to question number 2. Question number 2. All right. The addition principle of counting, right? So the addition principle of counting, principle of counting, and I usually call it as the art of casework. Whenever we think about casework, you got to think about all these like two phrases, okay? So you're going to perform casework anyway in the actual AMC 10/12 or AME, just doesn't matter, HMMT, ARML or PUMAC, any other test that you're going to take about, you guys will perform casework. So normally when we learn about counting, there are two branches of counting techniques. There's something called casework and there's something called complementary. When you look at the answer choices, when things are actually having like a lesser number of cases, well, lesser number of, like the answer choices, something like, like under 10, it's probably going to be best if you perform complementary. Or of course, like depending on the situation, you got to think about whether to perform the casework. But when you perform casework, because these are the set of questions that I actually got asked, during the offline classes, when I went over the weekend classes and whatnot, some students are actually asking me those questions. When do you use casework and complementary? You got to practice both first. But like we perform casework under one principle only. Here's what's up. These are the principles. I think these are the notes. Casework gotta be like performed, or it gotta be applied under two principles of comprehensive and exhaustive. So comprehensive and exhaustive. Sir, aren't they referring to the same thing? No, like exhaustive means that you got. All right, guys, let's begin with 25. Now we begin number theory. Types of primes. So how do we figure out types of primes? What do we know about primes? Notes. There we go. So number 1, primes can be actually classified as 2, 3, and 6k plus minus 1. So 6k plus minus 1 means that out of multiples of 6, you got to always watch it like 1 forward and backward. So something like 5 and 7, 11 and 13. But I'm not telling you that all those primes, all those numbers are becoming, primes at the same time. So what I'm saying is that if you look at 24, 23 is a prime, but 25 is not a prime. So there must be some exceptions, but normally all the primes that you look at is going to be of this form. And if you wanna wonder why that is the case, you can actually perform like otherwise, like think about it otherwise. What happens if you write it down 6k plus 2? That's multiples of 2. Like these are multiples of 2. What about 6k plus 3? That's going to be multiples of 3. What about 6k plus 4? It must be multiples of 2 again. So you can see that all those numbers are in fact, like somehow those are exceptionals. I mean, like, those are the reason why these are all excluded out of the ways. But again, like you just have to look at 2. That's the only even prime. Only even prime. And of course, this is the smallest odd prime. All right, so let me give you the second one. I need to talk about some parities. What are the parities? Parities means that evenness and oddness. Well, even numbers, like when we have some kind of difference of sequences and whatnot, a squared minus b squared, for instance, it can be actually written out a minus b times a plus b. And when you have a minus b and a plus b, do you understand that we have the difference of 2b, plus minus 2b? And those difference of plus minus 2b means that they share the same parity. So it's just going to be always odd times odd. Or it got to be even times even. So we have those two possibilities. It's got to be either odd times odd or even times even. That actually matters a lot because this question, 25, actually has to do with those, like parities. All right, so let's try to move on to this question, and we're not even guessing the answer. We're not even, like plugging the answer, plugging the numbers, or trying to check out what's going on here. We're just using the parities first. So here's what's up. I'm given solution. I'm given with n squared plus 5n plus 6. I got some n squared plus 5n plus 6, and I got to make sure that that's a prime number, guys. So in order to make this as a prime number, we're thinking, what happens if I multiply n? What if I plug n equals even? What if I plug n equals odd? But where's that intuition coming from? I think that intuition is, that particular intuition is never natural, but I think that the first factorization is more important. N times n plus 5 is way more important, way much more important, okay? So if you factorize it in this following form, try to think about it this way. If you multiply n times n plus 1, do you understand that this is always even number? Can you see that's always even number? Because think about it, if you're multiplying even number by odd number, because n plus 1 got to be odd number, different parities, it's always even number. And you can understand that becomes odd times even number, it becomes always an even number. Well, if I'm adding some kind of odd number right next to n, so something like n plus 1, n plus 3, n plus 5, n plus 7, or maybe you can think of n plus 2021, 2023, 2025, doesn't matter. But when you have those numbers added up right there, which is odd number, this is always even. And what happens? You're adding even by even to get even number. And the question states that that's supposed to be a prime number. How many even primes are there? There's only one even prime. Oh man, that's supposed to be 2. So we solved that n squared plus 5n plus 6 equals 2. N squared plus 5n plus 4 equals 0. N plus 1 times n plus 4 equals 0. N supposed to be -1 or -4. So if you take a square of this, that becomes -1 squared plus -4 squared. And if you add it up, 1 plus 16, it all becomes 17. Too easy, right? It's actually a nice question. Right. Let's move on to 26 as well. 26 involves something called greatest common divisor and Bezoos identity. Right, so since this is building up Bezoos identity, later on we're going to learn about something called chicken McNugget theorem. But, like when we go on to McNugget theorem, there's a huge difference between Bezoos and, like the McNugget theorem. But anyway, 26 right here. I would like to talk about some GCD. And I would like to talk about something called Bezoos identity. Bezoos identity is in fact a heavyweight. When I say heavyweight, it's a material that's gonna popping out as not as a major theme, but as some kind of helping tool in the very last step of problem solving for 20s or last 10s. If you went over all those past problems on your own, you might have seen the Bezoos identity popping out sometimes for GCD questions. So how do we understand what what this is? So normally when we get a times x plus b times y, and a and b are the fixed numbers, and a and b are the fixed number, we can actually write down the smallest possible numbers that can be written out is going to be the GCD of a comma b is multiple. That kind of makes sense though. I mean, think about it. We're gonna look at our question though. Solution. We got 30x plus 21y
And you can prime factorize this. Of course, you can prime factorize. And if you prime factorize, that becomes 3 times, well, not prime factorize. You don't need to prime factorize. Sorry. Like, that's just going to be 3 times 10x plus 7y. And x and y are just integers. However, I know that the conditions in the question stated that absolute value of x and absolute value of y supposed to be locked up between 1 and 5. So in other words, x can be just, like ranging all the way from, x can be -1, x can be ±1, ±2, ±3, ±4, and ±5, and vice versa. Y could be the same thing, vice versa, right? So check this out. We understand that this is going to be multiple of 3. We understand that that's going to be multiple of 3 because it's just a huge chunk of 3 times something, right? However, if you look at 10x plus 7y, it makes us think. 10 and 7. What's the GCD of 10 and 7? Well, the GCD of 10 and 7 is supposed to be just 1. So can I really make 1 out there? That's a question. Can I actually make 1 out of it? So I was thinking about, hey, what if I use all those numbers? How do I find it out? Well, of course, we're not using any, we're not even using the modular arithmetic or anything else, but we're just gonna plug the numbers in. All right, so imagine me plugging 1 and 2 and 3 and 4 and 5. So for instance, if I plug 10 times -1, can I make 7y equals 1? Well, I don't know. Like, that's going to be -10 plus 7y equals 1. So 7y equals 11. It's not going to be true. But what if I plug 10 times -2 plus 7 times, y? 7 times 3, I think, it's just going to be 1. So it makes sense. We can find certain solution. But what about like 10 times -3 plus 7 times what else? Like, can it work? I don't think it works out, right? I don't think it works out. So 7y equals 31. I don't get any integer solution. But what about like 10 times -4 plus 7 times y equals 1? 7y equals 41. Wouldn't make sense. 10 times -5 plus 7 times y equals 1. Y gotta be 7y gotta be 51. Wouldn't make sense. So I exhausted everything about -1s and -2s and -3s and -4s and -5. So I kind of noticed that x comma y that I just noticed, well, we get -2 comma 3, something that came out, but I'm not sure whether that's a unique solution. So I'm going to find out everything else right here. All right, I'm going to try out everything else right there, except we're going to see whether, we got to see whether these solutions are unique though. So y equals something. I'm going to say x equals 1. If I say x equals 1, 10 times...
Hello everyone, let's begin with question number 45, which is now geometry, right? So here's 45. This is about like variation of Pythagoras. So I think that, I have to teach you, or at least give you some kind of mentions about what to expect in, geometry questions. And plain geometry questions were normally in AMC 10 and 12. This is, by the way, the notes. Normally in plain geometry, geo, you are expected to find out Pythagoras. And there's something called similarity. And there's something called base area ratio. So we're going to study everything about Pythagoras, similarity, base ratio, and area ratio equaling with fixed heights, or we usually call it collinearity. And I'm going to teach you in these short lecture series what to expect. Pythagoras is going to be talking about length or area. And I guess this is also length, area, and normally this is also length, area. Then what about the other angle information? Well, angular informations are going to come out from just direct, just directly from triangular inequality, or triangle sum, or you can expect some exterior angle theorem, known as EA theorem,
Or oftentimes you can think about circles. Yes. And of course, if we bring it all the way up to like just AMC 12, we're expecting angular equation. Now, in this lecture series, in this must-know series, I'm not putting anything about like angular equation. I'm just focusing a lot on Pythagoras, similarity, base ratio, area ratio, and angular equations and whatnot. And I just want you to know about some Pythagoras. So this is the picture that you should understand. This particular picture that I'm drawing right now is going to be something that you should always have in your mindset, okay? So if I have some kind of length down there and a length down there, and you can always drop the altitude like this, well, for sure, let's just call it x, let's just call it y. Normally, that circular block squared minus triangular block squared supposed to be x squared minus y squared. This is always true, but why though? Because you can call it as h, because that circular block squared is going to be x squared plus h squared, and triangular block squared is supposed to be y squared plus h squared. And if you just vertical subtracting it, then you can get the above equations. And normally these above equations are typical set of Pythagoras variation that comes out in, you know, like the problem solving sessions. And I'll explain what these are in question number 45. So here we go. Let me erase all these notes. These were the required notes that you need to know. And let's go on to the solution for this problem. All right, so I want you to draw the trapezoid. And according to the trapezoid, we got AB in this following form, and we got some C right there, and CD given in this following form, and we got AD in that form. So these are the trapezoid, and we should expect that these are the parallel lines. Right, so AB is supposed to be 6, this is 4, this is 11, and we get AD equals 5. All right, so I need to find out the area of this. I think I need to find out the area. How do I find out the area? I think I need to know about the height. How do I know about the height? Well, you got to drop the altitude. And if you drop the altitude, let's just try to call it as h and h. And check this out. These are 6, right? And that must be 6 as well. So there's some kind of x. There's some kind of 5 minus x. And we have x and 5 minus x. And let me imagine cutting this outside. Let me pull this rectangle outside, and we eventually get a figure that just looks like something like this, 5 and 4. And there is h and x and 5 minus x, like this. Now, what does it remind you of? It reminds you of Pythagoras, variation of Pythagoras. And according to the variation of Pythagoras, we can actually solve this as 5 squared equaling x squared plus h squared. And you can also solve this as 4 squared equals 5 minus x squared. 5 minus x squared plus h squared. And if you subtract these two expressions, at the same time it becomes 9. And this is going to be something like 25 minus, actually 10x minus 25. Does that make sense? This is like 5 squared minus 4 squared, which is 9. X squared minus 25 minus 10x, which is plus 10x minus 25, and everything's gone. So we get something like 34 equals 10x. So x equals 17 over 5. So we got x equals 17 over 5 right here. So that shall be 17 over 5. Can we get what h is? Of course we can find what h is. So accordingly, we get 5 squared minus x squared, which is 17 over 5 squared, which is equal to h squared. So we get 5 minus 17 over 5. We get 5 plus 17 over 5. And that shall be 25 minus 17, which is 8 over 5. And we're multiplying this by 25, which is 42, I guess, 42 over 5. These are h squared. So I know that this can be written out as something like 4 times 2, and these are like 4 times, it's not 4, 6 times 7. Is this something that can be pulled out? 4 times 2 can be pulled out, of course. And these are 6 times 7. I don't think it can be anything getting pulled out. 1 times 21 probably. So it's going to be 4h must be 4 root 21 over 5. So we're almost done, right? We're almost done. 1 over 2 times 6, 1 over 2 times base, sum of the bases. And we multiply with the height, 4 root 21 over 5. And that shall be 17 times 4 root 21 divided out by 10. And you can cross out 2 and 5. It becomes 34 root 21 over 5. So if you add all these values all together, we get 34 plus 21 plus 5, 26 plus 34. It should be 60. Okay, so that's how we use Pythagoras, okay? This is how we use Pythagoras, and let's move on to the next page, which is, for me, it's next page, but next question, 46. Okay. So question 46 does talk about basic angle equation. Angle equation. What type of angle equation do we need to know? Well, here's the notes. First, please label some unknown angular information. And the reason why we label is because we want to figure out what's going to happen for angles, I guess, like literally. We want to set up equation. Set up equation or expression. But what type of equation are we expecting? Well, it can be Pythagoras, right? It can be Pythagoras. Probably it's very likely that it's going to be Pythagoras, or probably law of cosines for AMC 12. And probably it could be some similarity ratio. Similarity ratio, okay? So you might be expected to set up some ratio equations, or probably just law of sines. Law of sines. Or probably Heron's formula. There are so many, infinitely many equations and expressions, but these are everything having to do with lengths. But what about some angular equation? Well, angular equations, you are just using alpha plus beta plus gamma equals 180 at a time. Always, always. And the exterior angle, supposed to be sum of two remote angles. Two remote interior angles. So that being said, I would like to move on to question number, 46. I would like to delve into the solution. And it's not that bad, okay? It's not that bad. We can actually handle this. I'm going to draw the convex pentagon. So it can be any pentagon, an A, B, C, D, and E like this. And I want you to draw out all the diagonals, okay? All right, guys, let's begin with question number 57. All right, so 57 does talk about something called Sevians. And out of Sevians, there are lots of nice Sevians that you need to know. These are notes. Well, the first one is angle bisector. And I think that you are already familiar with angle bisector. And the second thing is median. And the third one is orthocenter, altitude. And usually those are, the Sevians. And what are the Sevians? Well, you can actually draw one vertex and connecting with any of the point onto the opposite side, and that becomes Sevians. Right. So out of those Sevians, medians are very special. Angle bisectors are special. Altitudes are very special. But that being said, I want to just talk about some properties of median right now. Now, when you see the medians, these are 2-to-1 ratio. Those are normal stuff that you already know, and this is from school. And the second one that you also know from, from median is that the area has been totally cut out into 6 equal parts. So 6 equal parts. And the last one, in fact, this is something that is new to you. It's using parallelogram. All right, so I want you to look at this question right here. Solution. AB. All right, so we got AB and AC. AB and AC. and BC. These are 7, these are 24, and these are 25. Imagine me connecting all the medians. Let G be the point. Let G be the centroid, and centroid refers to the point of gravity. If you sketch one point, and if you sketch another one, and if you sketch another one, we get G out there. All right, so I need to find out, again, the area of triangles formed by AG and BG and CG. That's an interesting fact. So I know, are you really gonna look out for all AG? Are you really gonna look out for everything about like BG or CG? No, you're not gonna draw any of those figures. However, I always want you to think about that whenever we are connecting with the midpoints, the median, you always gotta think about some parallelogram. But what type of parallelogram am I talking about? A parallelogram that can be extended. So you know that these are 2 to 1, right? So imagine extending it a little bit further, and if you extend it a little bit further such that this becomes the same length, we understood that AG is gonna have the same length as this one. So I'm just gonna call it as, well, let's say E. Why not? And if I get E, would you agree that this is CE is gonna be the same thing as BG? Because this is a parallelogram? Look at what happened here. Like, think about it. BC and GE, they've been bisected. Now, since they were bisected, you understand that this is going to be the parallelogram. So we understood that this is also going to be CG. So, in fact, I can actually write that AG is supposed to be GE, and BG supposed to be CE, and CG supposed to be just BE, I guess. And can we find the triangle formed by, like a triangle formed by those measures right here? Of course, we can think about those triangles. What is this? We can cut this particular triangle, again, any triangle, it doesn't matter whatever triangles that we have, as long as these are midpoints and midpoints and midpoints, we can usually call it as alpha, 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 and alpha, and alpha. We got 6 alpha total as 1/2 times 7 times 24. So if you cross it out, it becomes 84. So 6 times alpha equals 84. So alpha equals 14, I guess, right? Now, we're not looking for alpha, though. We're looking for 2 of these. But how do I know those are the same alpha? Because we understand that this area is going to be the same thing as this one, and also this one and that one, too. Why? Because it's always cutting out into the same part. Remember the base ratio equaling the area ratio? We can always get those areas are all equal with one another. So these are 2 alpha, in fact. So if that's 2 alpha, I know that CG has been used. I know that CG has been used up. I know that CE has been used up. Where is it? BG. And I know that this is AG has been used up too. AG has been used up. So the answer for this must be 2 times alpha, which is 28. Lovely question. Okay? So that is question number, something to do with Sevians. And hopefully I can give you extra notes. Not for just Sevians, but for something called, I'm not going to cover this as an example. I'm not going to cover this as an example or any of the problem sets. However, I think I need to give you the notes, though. So here's the notes. Still in the same problem, Sevians. These are something called Stewart's theorem. And Stewart's theorem is, in fact, it's heavyweight. And because it's a heavyweight, I need to explain what's going on here. The deduction, in fact, uses some trigonometry. But I'll write down everything, okay? So here we go. These are theta. These are 180 minus theta. You got to call this D. Got to call it M and N. The whole thing supposed to be A, and this is B, and this is C. So you can actually call this as capital A, capital B, and capital C, right? So what do you know from Stewart's theorem? Well, Stewart's theorem can be literally deduced quite fast using something called cosine theta is in fact equal to negative cosine 180 minus theta. And you can rewrite this as something like cosine theta as 2 times d times m, d squared plus m squared minus c squared. And negative, you can also rewrite it as 2 times d times n. And this is going to be d squared plus n squared minus b squared. But out of all doing like some algebraic bashing, you guys will actually get some kind of interesting, like the fact about Stewart's theorem. And it's easy to remember. Dad, actually, it's not dad. It got to start from man. Man and his dad, they put a bomb in the sink. So this is going to be always true for, anything that you see for the Sebians. But you shouldn't always think that this is going to come out. Well, this is already heavyweight again. Now, it's being deduced using law of cosines or, just some trigonometric angular equation, so that's hard. But who knows, like it can come out in AMC 12, it can come out in AMC 10. But we don't know that, but you have to be able to notice. Some people call it as an Apollonius theorem. Some people call it as a Stewart's theorem. But I usually call it as a Stewart's theorem. And I remember this as man and his dad, they put a bomb in the sink. Just think about like movie, a Hollywood movie scene that begins from the very early start, that they got a building outside, a dark building, and in the dark building, the man and his dad, they literally put a bomb in the sink and they blow up the whole building and the movie begins. You can always think about those logic here, and that's what's up for Sebians. Extra notes, okay? These are extra notes. And let's move on to the next question. Now, this is my favorite MPG. 58. These are mass point geometry. Okay, this is my favorite. Mass point geometry. Mass point geometry is always going to be used in this following setup. Please write down notes. Especially when we get certain figure like this. When we get certain figures like this, we can always use mass point geometry, okay? Now, mass point geometry, the whole idea is we put a mass on each vertex for seesaw. We're expecting a seesaw effect. And when you think about the seesaw effect, I'm not sure, I'm not a physics major, but I think that you might have seen something like this in some kind of science book when you were young. We have some kind of momentum, like moments or momentum, or I guess we call it moments, on top of that, like the seesaw, and we put the heavy weight, closer to the moments, and we put lighter weights. Hello everyone, let's begin with question number 85. Okay, 85. It's application of floor function, okay? Application of floor function. So what are the floor functions? Floor functions, the key notes that you should make is that whenever you see that floor symbol, you always have to break down multiple cases of integer expressions or integer intervals. So casework on the integer interval. So if I show you that, like something like the floor of 1.23, you know that these are 1, right? But what about floor of, like 1.23, negative 1.23? So I normally say this in like using some example about going to the mall. Imagine you have to go to the parking lot, and the parking lot is in the underground. And imagine you are taking the escalator, not the elevator, but escalator, that was stuck between B2 and B1. You know that negative 1.23 is stuck between B2 and B1. And if the protocol of those like security tells you always you have to go downward, then where would you go? Would you go to negative 1 or negative 2? Would you go to B1 or B2? If you have to go down, if you have to go to the floor, you will actually go to the floor, negative 2, B2. That makes sense, right? So if you are stuck between that first floor and the second floor, on the escalator and you have to go down to the floor, so to speak, of that particular, like the floor that you're in, then you would probably go into the first floor. So these are, this is what's going on here. However, I should actually show you what to do with those, the different functions, I guess. And check this out. I'll give you some, I think that I should show you with solution real quick. All right? Solution. Why not? I want to graph y equals this one. And I want to compare this, y equals 1 over 2. I want to compare this with this one. What the heck is this? Well, that decimal part or the remainder part or yes, I usually call it the remainder part or the decimal part, that becomes x squared minus the floor of x squared. This looks so crazy hard, but don't panic. I'll show you what's going on here, all right? So check this out. Imagine you sketch y equals x squared. All right, you imagine you sketched it, and we get 1, 1, and 2, and 4. And that's enough. I mean, these are the enough information. Okay, so imagine we put a dot here, and we put a dot there, and a dot right there. I told you that we need to perform something called casework on the integer interval, right? I'm going to sketch the floor part of it, okay? The floor part of it, and check this out. What it means to casework on the integer interval, it means that you got to cut down the graph with the lot of horizontal lines. You got to draw a lot of horizontal lines. And you keep drawing all those lot of horizontal lines like this, and you keep drawing all those horizontal lines, everything that were stuck between 0 and 1 will be copied, will be just, will be called as 0. And everything that was stuck between 1 to 2, for this floor part, I'm just going to call this as 1. And for something that stayed between 2 and 3, I'm just going to call this as 2. And something that's stuck between 3 and 4, I'm just going to call this as 3. And we continue doing this part on and on and on. And you can see that these horizontal line segments are getting shorter and shorter and shorter. Why? Because it gets steeper and steeper and steeper. In other words, as a quadratic function goes up, from 1 to 2, the amount of exchange it requires gets shorter and shorter and shorter at a time. Now, I want you to think about what happens if I take the difference between the x squared and the floor function right here. If you take the difference between x squared and the floor function, would you notice that I'm just going to push, I will sketch this part, and I'll sketch that part downward, so that it's going to be sketched all the way down here. And this little part is going to fall underneath, and this little part is going to fall underneath, such that everything that I thought which should stay in the second floor and the third floor, everything dropped down all the way onto the x-axis. It dropped down all the way onto the x-axis, so whatever that you sketched right here will be actually covered right there. So it's going to be, it's going to fall downward. And whatever that stayed on top from 5 to 6, it's also going to get dropped all the way down here, and it keeps getting dropped. Now, here's what's going on. I told you that we need to perform the casework on the integer interval. And you can actually find some nice caseworks. So in other words, when you're computing these functions, don't panic. You got to just break it down into x equals 1 and x equals 2, or y equals 1 and y equals 2. However you perform caseworks, it always got to be into the integer interval. And if you perform the integer interval in between x equals 0 and 1, we just have one branches that looks like this. One branch that looks like this. In between 1 and 2, we got 3 particular branches. Now, in between 2 and 3, what do you think? How many branches are you expecting? I got 1, I got 3, and I think that I'm going to get 5 of those. Yes, we get 5 of those. So we keep getting all those 5, and that shall be the sketch that are stuck between 0 and 1 though. 0 and 1, everything gets stuck, and we're making it fall as if we're playing Tetris. If you're playing Tetris, things that are falling, if you click enter button, it just falls down super fast, right? It just, what it does for the Tetris. It's gonna be the same thing, okay? Now, we have 1 of those, we got 3 of those wedges, so to speak, and 5 of those wedges, so to speak, and all the way down to where? I think I need to go all the way up to 9 and 10. So how many wedges am I expecting here? Well, I'm expecting, like, I got 1 of those, I got 3 of those, I got 5 of those. So it seems like I'm multiplying, like 2. Well, you can see that I'm multiplying. Shall I say, yes? Shall I even color this with yellow so that you can see what's gonna happen? For this one, it's gonna be 2 times 1 minus 1. For these 3, it's gonna be 2 times 2 minus 1. They're 3. For these 5, it's gonna be 2 times 3 minus 1. There are 5 of those. So how many wedges are you expecting here? 2 times 10 minus 1. 19 of those. And in fact, we're solving y equals 1 over 2. Oh, so y equals 1 over 2. So if I draw y equals 1 over 2, it seems like I need to count 1 of those, and 3 of those, and 5 of those, and 7 of those, and 11 of those, all the way up to 19 of those. And guess what? I'm adding all those solutions. I'm adding all those solutions up to 17 and 19. And I know there are 10 of these. I know these are 10 of these from 0 to 9. There are 10 of these. And I'm adding 1 by 19, which is 200 over 2. I get 100 solutions. Lovely, right? So this is how we solve 85. Okay. So now I'm going to try to teach you one more thing, 86, which is drawing composition of functions. It came out, like similar questions came out, and for this one too, it's coming out not just in AMC 10 and 12, but it's also coming out in AMY, I should be able to graph it, and especially on AMY. If you move on to AMY, then you will see some logarithm function with the floor functions in it, but still the logics are the same, okay? So 86, here we go. Question 86, these are graphing composition of functions. All right, so check this out. We have y equals solution. I think that I need to show you with solving mechanism. I should show you the procedure, not like just teaching materials, because there's not much of a thing to teach here. The only thing that I need to mention is that composition of function, we just have to graph with separate domain. Domain and range. And I should say, I'm going to talk about something called